Hey everybody, welcome to the last video in this series. This is our section 2 part B of our AP Calc BC practice test. Here in this section we'll do 4 FRQs and they are all non-calculator. So let's get started on number 3. So we got the graph up here and it is the velocity graph. Alright, so that's really important to note that we're looking at a velocity graph. So once the acceleration of the particle at 5.5 seconds. So 5.5 is here. So it's this point on the graph. Well, the answer is not 2 because that would be the velocity. So what we need to realize here is that the acceleration is the derivative of velocity. And derivative is slope. So what we really need is just the slope of this line would be a of 5.5. So a of 5.5 would be v prime of 5.5, and the derivative is the slope. So all I need is the slope, and I can just say I go up 2 over 1, so the slope is 2, and the velocity is measured in meters per second, so this is meters per second squared. And that is all we have to do for that one. So now on to part B. Find the value of the integral from 0 to 10 of velocity. And then we'll talk about the meaning of it. But what we start with here is the integral from 0 to 10 is the area under the curve from 0 to 10. So we have a bunch of shapes here. So we start with our semicircle, all right? So I want to find the area of the semicircle. This semicircle has a radius of 1, so that means pi r squared is pi times 1, so that's pi would be the whole circle. If it's a semicircle, that part is pi over 2. Then I got a triangle down here, and the area of that is going to be 1/2 base times height. Well, the base is 2, height of 1. 1/2 2 times 1 is 1, but the area is below the x-axis, so I'm going to make that -1. Then let's go with, I guess we could just do this little triangle here. So that's going to be 1 times 1 is 1, half of that is 1/2. And then maybe we'll do, let me think about this. No, I'll just go, I guess there's a bunch of different ways. I definitely want to do this. So this is 4. And I definitely want to do this. So this is 1 times 2 is 2, so that's 1. I'm just trying to think of the best way. That I'm overthinking it at this point. Right now I'm wasting time. I'm doing the thing that I tell students not to do. So I'm just going to do it. And even if you disagree, then you come up with a different way. So I'm going to do this. So I get a trapezoid here and I get a trapezoid here. So this trapezoid is going to be 1/2 base 1 plus base 2. So base 1 is 1. Base 2 is 3. 1 plus 3 is 4. Half of that is 2 times this height, which is really 1. So that's 2. And then this one is going to be, you might even just be able to see that it's 2.5, but it would be 3 plus 2 is 5. 5 divided by 2 is 2.5 times 1 is 2.5. So all together, add all the numbers together. So this 1 and this -1, they cancel out. So they're gone. So, and this is 3, 7, 9 plus pi over 2. And the meaning of it. So what an integral, the way you find it, it represents the area under a curve. But what it means is it describes the function above it, which, let's say the antiderivative is the one above it, and I use the word below for like the derivative. So the function above it, it describes how that function changes on this interval. All right. So it really just represents the change in position from 0 to 10. I'm going to call that displacement. So it's displacement during t equals 0 to t equals 10. So it's just the particle's displacement. All right. Moving on. All right, so if you're watching on YouTube, then you just saw this. So I'm going to write these real quick. If you are watching on TikTok, then this is a whole different video. So you can go back to the last video to get these values real quick. So this was pi over 2. This was -1. I'm now going to consider it +1 because we're finding the integral of the absolute value. Then this one was 0.5. Then this one was 2. Then this trapezoid was 2.5. Then this was 4. And then this was 1. All right? So all I'm really doing is these ones don't cancel now. So now the integral from 0 to 10 of the absolute value of velocity is just equal to 11 plus pi over 2. So in the other one, we got 9 because these ones canceled. Now they don't because this one is considered a positive one. And that represents, so what that represents is the total distance traveled. The total distance traveled from t equals 0 to t equals 10. So that's the major difference here. The integral of velocity is displacement, and the integral of speed, or the absolute value of velocity, is total distance traveled. All right, again, and if you're watching on TikTok, you can watch the video before to see just how I got these, because I explained them, and I probably over-explained them. All right, moving on. Part D. At what time does the particle change its direction? So the way we want to think about this is it changes direction when velocity changes either from positive to negative or negative to positive. All right, so velocity describes its speed and its direction. So positive is one direction, negative is the opposite direction. And what we're doing in those, we just want to know first, well, when does velocity equal 0? And in addition, when does it change direction? So when does it go either from above to below or below to above the x-axis? That is when we're looking at a velocity graph. So that means it occurs at 2 and 4, because at 2 it's positive before and negative after, and 4 it's negative before and positive after. So that's at t equals 2 and t equals 4 is when the particle changes direction. All right, moving on to number 4. So we want the area of R. So the way I find the area between two curves in rectangular coordinates is I just take the integral from 0, because this is clearly 0, 0. I need to find this intersection point. So what I want to do is set these equal to each other. So 8 root x equals x squared. I think I'll square both sides, so I'll get 64x equals x to the 4th. Bring everything to one side, so 0 equals x to the 4th minus 64x, and then factor out an x, and I get x, and then x cubed minus 64. I am going to say that this is 0, and then this is clearly 4, because 4 cubed is 64. I could factor that further, but if you know how your difference of cubes work, I'm just going to factor out an x minus 4, and then what's left is never going to give you a real 0 anyway, if we remember that from pre-calc, so I'm going to skip all that to save time, because there's enough to do in this problem. And I'm simply going to see that it's just 4. And then I want to do the top minus the bottom. So f of x minus g of x. So I'm going to say that's 8x to the 1/2 minus x squared. I'm putting it to the 1/2 because I know I'm going to be taking the integral, so I might as well just write it that way and save a little bit of time. So now I'm going to take the antiderivative, which means I add the exponent to get 3/2, and I then divide by 3/2, which is like multiplying by 2/3. So I'm going to get 16/3 here. And then x squared is simply 1/3 x cubed. Then I'm going to evaluate that from 0 to 4. Notice when I do plug in 0, I'm just going to get 0. So all I have to do is plug in 4. Again, the quicker we can do these in our head, the better. So if I plug in 4 to the 3/2, let's remember do the square root first to get 2. And 2 cubed is 8. 8 times 16. Oh, that's a tough one. That's just going to be 128. But that's not fun to do, no calculator. So yeah, 128, and then a 4 cubed is 64, so 64 over 3, and 128 over 3 minus 64 over 3 is 64 over 3, and that is the area. Now we move on to part B. And what we can see is we want the volume of the solid generated when it is revolved about the y-axis. Okay, this is pretty tough. So revolved about the y-axis, I want to look at it like this. So I'm going to be moving it like that. So what I have is I have a big R and a little r. All right, ignore this capital R, which is they meant was the area. We already found that. So I got a new big R, which is the radius of the function that's further away and from our axis of rotation, which is the y-axis, which means I'm integrating in terms of dy. So I'm going to set up my integral like this. So I'm going to say my volume is equal to pi times the integral. So now we've got there's a little gap here, so we've got the washer method. And that means that we are going to be doing pi big R squared minus pi little r squared. Now this is where it gets a little bit tricky because big R is the one that's further away, so that's g of x. But g of x is really y equals x squared, but I need it x in terms of y. So root y equals x. So now I have I'm going to actually write this. I have root y squared. I realize that is just y, but this one I really want to illustrate so that everybody can see like what's happening. And then I got to go to the other one, which is f. That's the inside radius, the little r. And that is where I have y equals 8 root x. So I have y over 8 equals root x, and then if I square it, I get y squared over 64 equals x. So now I'm going to have y squared over 64 squared. So big R squared minus little r squared, and now I have dy. So this is the integral that I have to evaluate, which non-calculator does not look fun. But we're going to do it anyway. So let's take a look here. So, whoa, my bad. I forgot probably the most important part. So I learned before that this was 4, but I need the intersection at the y. So just plug 4 into either one of the originals. So this one's easier. 4 squared is 16. So I'm integrating from 0 to 16. So now I'm going to simplify this. This is just y, so that's pretty cool. And then this is y squared, which is y to the 4th. And then y to the 4th over, I am not going to do 64 squared. I highly doubt you'll be expected to do that. I don't know what that is off the top of my head, non-calculator. I mean, I do know it's 2 to the 6th squared, so it's 2 to the 12th. But I don't know that. So I'm going to leave it. And then we keep going, and we've got pi times the antiderivative of y is 1/2 y squared. And then this is going to be y to the 5th over 5. So I'm going to get y to the 5th over whatever 5 times 64 squared is, which again, I am not going to do that since it's non-calculator. And I'm evaluating from 0 to 16. And finally, we are going to do pi times, well, this is going to be 16 squared over 2. Well, I could do some work here. I mean, 16 is 2 to the 4th, so this is 16 squared, which will be 2 to the 8th over 2, which is 2 to the 7th. That one I do know is 128. And then I have 16 to the 5th. Well, 16 to the 5th is going to be 2 to the 20th. Let me make sure I'm doing that right. Yeah. 2 to the 20th, and we already said that 64 squared was 2 to the 12th, so that's 2 to the 8th, which is 256 over 5. And then 0 is just going to give us 0, so I just get this. I am going to just leave it that way. I think we could get a common denominator, but I am not thinking that you would ever have numbers like this. So I'm just going to stop there. The point of this is not to do all that like stuff even that I was doing in my head. The point of it is to understand how you set up a washer method when it's revolved about the y-axis. So the two things to look out for is make sure you get the bounds in terms of y, and make sure you get each equation in terms of y, so you solve for x. And again, the rest is, in my opinion, this problem is just kind of ridiculous for a non-calculator. But some of that was fun to do in our head, and then you get to a point where it's just like not necessarily, you would just never want to spend that much time on an AP problem. But again, concepts are more important now. I doubt you'll see that on the actual AP test, but these concepts, I'm certain you will. All right, on to 4C. So the base of a solid, okay, each solid perpendicular to the y-axis is an equilateral triangle. Let's pretend that's equilateral. So this is super helpful if you know the area of an equilateral triangle. I'm going to prove it here really quickly, but if you just know this is a formula worth knowing in case you get a question like this. We know that the angles of an equilateral triangle are all 60. So therefore, when I drop this altitude, I have a 30, 60, 90. And if I say that, I'll call it S. S is the side length. So that's the S over 2, and this would be S root 3 over 2. And then the area is simply going to be 1/2 the base, which is this S over 2, times S root 3 over 2. So you get root 3 over 4 S squared. If you can commit that to memory, I think that's worth it. Just again for this test, to just be able to just whip that out and say, okay, they are talking about the equilateral triangle. I know this is the area. Okay, so now what S is the side length. Well, that is g of x minus f of x. Well, we did this in the last problem. G of x, we would get x by itself. It's really g of y, I guess we could say, is root y, because y equals x squared, so root y minus, then this one we did in the last problem, which was y squared over 64. This one, luckily, we do not need to evaluate, so we don't have to worry about the absurdity of that last problem. And we just need to set this up. So what we're going to do is we are going to say that our volume is the integral. So again, we're integrating with respect to y. We saw in the last problem that this was 0 to 16. And then I have root 3 over 4. I could have brought that out in front, but I just didn't think of it, and I don't have space now, so I'm just going to put it here. And then it's s squared, and s is root y minus y squared over 64, all squared, and then it's dy, and that's it. That is the integral that we have. All right, on to the last part of number 4. All right, the line tangent to the graph of x, of f at x equals 1 is parallel to the line tangent to the graph of g at point Q. Find the coordinates of point Q. All right, so just to visualize this, we've got some line here that's parallel to some line here, and we want the coordinates. We'll call this Q, and this is... Wait, the line tangent to the graph is parallel to the line tangent... Okay. Oh, at x equals 1. So this is like 1 comma... Well, for f of x is 8 root x, so this is just 1 comma 8. And then I'm looking for the coordinates of Q. So what I have here is if the lines are, if they're parallel, then that means their slopes are the same. So if I start with f of x and I take the derivative, well, the derivative of 8 root x is, hopefully this is another one that you see a lot if you can commit this to memory. The derivative of square root x is 1 over 2 root x. So I get 8 over 2 root x, which is 4 over root x. If you don't remember, that's fine. Just make it x to the 1/2 and just do the power rule. And I want to know the derivative. So I want to know f prime of 1, which is 4 over 1, which is 4. So that means that the slope of this line is also 4. Well, the derivative of x squared, so g prime of x is equal to 2x. And if I want to find the value of x that would give me this same slope of 4, I just set that equal to 4. So clearly that happens at x equals 2. So my coordinate is 2 comma, and then I plug that back into g, and 2 squared is 4. So the coordinates of point Q are 2 comma 4. All right, so not at all related to the last several problems, but they do that a lot. They'll throw in like a last part that just tests another concept, but it's based off of like the same given information. So don't be surprised if you see something like that. All right. On we go to number 5. So we have, there's a little dt here that got cut off. We're looking for a particular solution here. So this is going to be separation of variables. So we're solving a differential equation. So what I'm going to do is I'm going to do dp over 500 minus p is equal to 1/10 dt. I do that so that I can integrate both sides. And the integral of this is the integral of 1 over something is the ln of the absolute value of that thing. And then if we think about if we took the derivative of this, we would get 1 over 500 minus p, but I'd have to multiply by a -1. So I need a -1 out here to kind of cancel that so that there is not 1 up here. And then on the other side, I get 1/10 t plus c. And then I'm just going to do a little bit of rearranging. So I'm going to divide through by the negative. So I get the ln of 500 minus p is equal to -1/10 t, still plus c. If I divide c by a negative, it's just a different constant. So I'm just going to keep absorbing the constant here and keep calling it c. And then I'm going to exponentiate. So I'm going to do e to both sides. E to the ln essentially cancel, and I get 500 minus p. And then I have this. I have e to the -1/10 t. But when I add, that's like multiplying by e to the c. But the e to the c is just another constant. So I'm going to write it as c e to the -1/10 t. And if that didn't make sense, let me just explain that again up here. I made it e to the -1/10 t times e to the c, because if I did multiply like bases, I would add my exponents, which is where that plus is, and then e to the c, I just called a new c, because e is a constant, and a constant to another constant is a new constant. And then if I rearrange a bit, if I imagine the p coming over here and this whole thing coming over here, I get p equals 500 minus c e to the -1/10 t, And my initial condition somewhere up here is there's 100 at time 0. Well, when I plug in 0, e to the 0 is 1, so 500 minus c is 100, so c must be 400. So p equals 500 minus 400 e to the negative 1/10 t. All right, so again, I plugged in 0 here. That became 400 equals 500 minus c. And that's where oh, my bad, 100. I had 400 stuck in my head. 100 was the initial amount. So this is 100 equals 500 minus c, so c is 400. So the particular solution is this one at the bottom, and that is all they were asking for in part A. So now we move on to part B, and we've got our same differential equation, and we want to find the limit as t goes to infinity of p of t. So I think it's easiest if we just go back to, so you can, again, on YouTube, it's the one I just went over, but on TikTok, it's the last video. So I'm finding the limit as t goes to infinity. I'm just going to put, this was the answer to part A, which we just did. All right. The way we kind of analyze this is, one thing that you really should know is what the graph of e to the x looks like, which is like this. So when I imagine a kind of you don't evaluate infinity, but when you kind of substitute a really large number in here, you're going to get e to the negative infinity, which means that's the graph of e to the x going to negative infinity, which you can see has a horizontal asymptote at 0. So this whole term goes away, and all you're left with is the 500. That's it. That's all I got to do for that one. All right. Oh, I think I went too far. So if we look at part C now, so I'm trying to think of the best way to go about this. All right, I'm going to just take our answer from, again, part A, which was 500 minus 400 e to the negative t over 10. And I'm just going to find the second derivative. So p prime of t is, so what I'm going to have, 500 goes to 0. I'm going to have e to the negative t over 10 times the derivative of that, which is negative 1/10. But negative 1/10 times negative 400 is 40. And then if I do p double prime, of t is, again, e to the negative t over 10, and the derivative is negative 1/10 times 40, which gives me negative 4. And if t is e, okay, so e to any power is positive. That doesn't matter that it's a negative exponent. It's just a fraction. So this is always positive. Because again, in the last problem we saw, when we just look at the graph of e, it looks like that. And a positive times negative 4 will always be negative. So p double prime of t is always less than 0, which means it is, yes, always concave down. All right, so let's move on to this one. This one's interesting that they asked both of these in the same problem because they look very similar, right? But they want this in terms of p. I'm going to show you another way to do it. The way we did the last problem is I just started with p of t and just took, two derivatives. Here I want the second derivative too, but I want it in terms of p. So we could take our last answer and kind of do a little bit of algebra, but I'm just going to go from here. So if I want to find the second derivative, that's just the derivative of this. That's 1/10. Nope, that is not 1/10. I guess, I guess I could look at it that way, so let me do that. So it's 1/10 times the derivative of this. Well, the derivative of 500 minus p is negative dp dt. Right? The derivative of p is dp dt. So I really get negative 1/10 dp dt. All right? But I want it in terms of just p. So that's negative 1/10 dp dt, but dp dt is 1/10 500 minus p. And then if we just clean it up a little bit, I would say our final answer is negative 1 over 100 times 500 minus p. So that is our second derivative in terms of p. And if we use some logic from before, we figured out that the limit as t goes to infinity is 500, and its initial value is 100. So it's the population will always be between 100 and 500, and so that means this value will always be positive, which means this will always be negative. So is the value always positive? The answer is no. It is always negative. Which we knew in the last problem, we showed it just in a different way. All right, on to our last problem here. As always, your number 6 is typically, maybe not always, but almost always, it is going to be a series problem. So if we have the Maclaurin series for 1 over 1 plus x, which is just the alternating geometric series, starting at 1 with a common ratio of x, I stand corrected, a common ratio of negative x if it's alternating. Write the first 4 non-zero terms and the general term of the Maclaurin series. So we're going to do this. We're going to say 1 over 1 plus 2x is approximately, because I'm only going to give the first 4 terms. And what I'm going to do is I'm going to say that I'm replacing x with 2x. So that means I'm replacing each x with 2x. So I have 1 minus 2x plus, well, if I replace x with 2x and I square it, I get 4x squared. And then if I do the next term, the fourth term, that is minus x cubed. Well, if I cube 2x, that becomes 8x cubed. And then if they want the general term, I'm going to say plus dot dot dot. If I go here, the general term is negative 1 to the n. And I'm just, again, replacing x with 2x. So I have 2x to the n, which you could write 2 to the n, x to the n. That's totally fine, but I think that this is also acceptable. All right, let us move on to part B. Find the radius and interval of convergence for f. So we could do the ratio test, okay? But if we realize that this is a geometric series, all right? And a geometric series is whenever the common ratio is between negative 1 and 1, all right? So what we know about a geometric is if the common ratio is between negative 1 and 1, well, our common ratio here is negative 2x. It's kind of like our common ratio here is negative x. So if I just replace x with 2x, I get negative 2x. And then all I have to do is solve that. So if I divide everything by negative 2, I get 1/2, flip the sign, negative 1/2, but then flip everything back so it reads left to right. So I get negative 1/2 is less than x, which is negative less than 1/2. I also know the center is at 0. So this is the interval of convergence, and the radius of convergence is just 1/2, because the distance from 0 to 1/2 or 0 to negative 1/2 is positive 1/2. So this gives you both. Again, you could do the ratio test, but I think when it comes to geometric, I like doing it that way. All right, and or not the last one, but next one, number 6. So we want this to be the third degree polynomial for g if g is the integral of f. And then we're going to find 1/4. So what we can do here is just kind of write out again what we had for f. So the third degree, so if we're going to be, let me think about this. Yeah, I only want the third degree. So I only need to go to the second degree. So what we found in an earlier problem was that we got 1 minus 2x plus 4x squared. That's all I need for this because all I'm going to be doing is I only want to go up to the third degree. And g of x is the integral of this. So if I want g of x, and I guess technically if they want f of t, let me just make this, I guess, like mathematically correct. These should be t's. And then if I want to integrate that, then I just get x minus x squared plus t cubed over 3, so 4/3 x cubed. And that is our third degree Taylor polynomial. So that's why I stopped at squared, because if we need third degree and I'm integrating and I'm going to be adding to my exponent, then I know that I can just stop there. All right, so that's my third degree Taylor polynomial approximation of g. And then if I want to find the third degree evaluated at 1/4, that is simply just plugging in 1/4 to this. So that's 1/4 minus 1/4 squared is 1/16 plus 4/3 times 1/4 cubed, so that's 1/64. And then I guess I could cancel this to get 16. So then I get 48. So if I want everything in terms of 48, 1/4 is 12/48 minus this is 3/48. And then right here I have 1/48. So 12 minus 3 is 9. 9 plus 1 is 10. 10/48 reduces to 5/24. And that is our answer for that one. All right, we're getting to the end here. We got 2 more parts. All right, so now I want to find the fourth derivative of g at 0. So now with g, we want to think about what g is. So what I'm going to do is rewrite what it was from before. So it was x minus x squared plus 4/3 x cubed. And then what happened was, so I stopped in the problem before, but I should keep going. So if we refer back to f, the next term, so I'll double back to it now. The next term that we found was minus 8x cubed. So if we do the antiderivative of that, that would be 8x to the 4th over 4. So that would be minus 2x to the 4th. So I do need that for this problem. And then I think that's all that I'm going to need. And because what ends up happening is I could do this a couple different ways. If you think about how you build Taylor series in general, so in terms of g, what it would be is it would be g of 0 plus g prime of 0x plus g double prime of 0 x squared over 2 factorial. And then I am gonna keep going here. G triple prime of 0 over 3 factorial. And finally, you'd have G, the fourth derivative of G at 0, which is what we're looking for, times, whoops, this one I missed an x cubed, my bad. You get an x to the fourth over 4 factorial. This is just how you build a Taylor series. So that means that if we did it a different way, but this should still be represented by this, all right? And the x to the fourths are not useful. We're only looking at the coefficient. So that means -2 must be the fourth derivative evaluated at 0 over 4 factorial. And then I can simply just multiply. 4 factorial is 24, so I get the fourth derivative evaluated at 0 would simply just be -48. Another way to do it is to just take the fourth derivative of this, which seems like a lot of work, but if you realize that these are all just going to disappear because they'll eventually be constants, and what this ends up becoming is -2 times 4 times 3 times 2 times 1. All those coming in front, power rule over and over again creates a factorial, and you might be able to figure out in your head that it would be -2 times 4 factorial. But if that doesn't make sense, then just do it this way. Just know what a Taylor series looks like and match up the term, and then that's how you solve for this. All right, on to our last part. So this third degree Taylor polynomial, let's refresh what that was. That was from an earlier problem. So again, on YouTube, we just did it, but on TikTok, look back a couple videos. I think it was part C. We found the third degree Taylor polynomial about G. And all we did was we plugged in like 2x here to figure out what f was, and then we took the integral or the antiderivative, and it gave us, let me find that, it was x minus x squared plus 4/3 x cubed. All right. And then what we did in another problem was, in the problem before, we found what the next term would be. So I can just jump back here. We found that that would be -2x to the fourth. So one thing to notice, if we want the error bound, then what we can do is we can simply just since it is alternating, I know it says use Lagrange, but honestly, like if it's alternating like this, right, then we can just use the alternating series error bound, which is easier than the Lagrange error bound. And all that is it's the error bound is the next, like the first unused term. So if we kept going, we figured out that the next term will be -2x to the fourth, and it's the absolute value of that. So the error is going to be less than, so like this thing here, is going to be less than 2x to the fourth, because it's the absolute value, and x is 1/4. All right, which that's equal to 1/4 to the fourth is 256. 1 over 256 times 2 is 1 over 128. And 1 over 128 is less than 1 over 100. So that shows that our error is going to be less than 1 over 100. All right, so I would just use alternating series error bound for that. You certainly can use the other one, and you will get the same answer. But to me, alternating error bound is easier because it's just the first unused term. It's easier to remember. Okay, that is the end of this practice test. I hope you found everything useful. Let me know in the comments what other kind of tests you want me to do, or if you would do any problems differently, or if you found any mistakes. I would be open to that too. All right, hope that helped.